You are listening to the Wi-Fi Ninjas podcast, where we talk about wireless technology. Here are your hosts, Mac Daring and Matt Starling.
Hello, and welcome to the Wi-Fi Ninjas podcast / videocast, depending if you're just listening to us or if you're watching us. Very excited about this one today because we have a very special guest on from a company called WISER. There's a guy called Logan. But first, Mac, how are you?
I'm very good. Thank you very much for asking. So, guys, it's a really massive pleasure to have you on. As you might know, we might be quite interested in the RTLS. This is our secret passion that we've been doing for at least several months now. So we are extremely happy to have you on. So, guys, how are you doing, Logan?
I'm doing great, all things considered. It's been a strange year, but I can't complain.
And you're over in the US, right?
Yes, we're based in Raleigh, North Carolina, East Coast.
Very nice. So if you could just give the listeners or viewers just a little bit of background about yourself so they can understand a little bit more about you.
Sure. So individually, I went to school around here. So I was raised in North Carolina. I went to North Carolina State University for engineering. It was not electrical engineering, so I won't be able to get too in depth on those matters. But I went to school for engineering. I got passionate about startups and entrepreneurship. Attempted to kind of create my own company out of school, which was an abysmal failure. But you learn a lot from those. So moved on from that to this role, just trying to kind of help this start from the ground up. So it was the two founders of WISER Systems and myself. And then from there have kind of grown into a deployment, a product manager, and some of kind of technical sales special projects role.
Amazing. And we have another guest, but he's kind of just lurking in the background, ready for the demo. So a guy called Steven. We're very lucky that we're going to be able to see a live demo of the WISER solution later on in the video cast. So if you guys are listening to the audio only of this, I do encourage you, when you get back to your PC or phone and you can and it's safe, do have a watch of the final part of this episode so you can see the WISER solution in action. We've seen some snippets of it and it's very, very impressive. So we've got a helper in Stephen a little bit later on. He'll be showing his camera and doing some walking around for us so we can see some ultra wideband in action. And as you guys focus mainly on ultra wideband, right?
Yes. Yeah. Our core IP, our core patents are around algorithms to tame reflections and multipath in crowded spaces. So ultra wideband makes the most sense for what we're doing right now. It's not something we necessarily are irrevocably tied to, but it definitely is what we're using now and in the foreseeable future.
Sure. So is there anything else about WISER you just kind of wanted to let everyone know about, or are you happy to move on?
Oh, well, we're happy to work with anybody. We're US based. We're certified for use in North America. We'll be certified for use in Europe this year. It's pretty soon. And a small company, we're a prime defense contractor, woman owned, certified small business. So, but that's the sum of it.
Okay, and you mentioned you are working in crowd spaces using ultra wideband. So what do you mean by crowd spaces? What verticals do you mainly target, and why do you target these verticals? And also, since we are there, let's also try to sneak in some information why ultra wideband is best suitable for these scenarios.
Sure. Yes. So when I talk about crowded spaces, I'm essentially talking about areas and facilities, industrial environments where you don't have a lot of direct signal path. And so there's a lot of piping, or there's machines creating noise, electrical noise. There's ladders, there's racking, there's things in the way. And so it becomes very difficult for sensors to do location, because a lot of that is determined off signal strength or timing information. So it really requires kind of a direct point-to-point measurement be made. And so when there's a bunch of reflections scattered around the space, it becomes increasingly difficult to find the true signal versus reflected noise. Basically reduces my signal to noise ratio. So WISER has been picked up. Our main biggest focus area where people are interested in us right now is where other technologies don't work. So they've been frustrated, and then they've found us, right? So these are areas where lots of metal, lots of reflection, lots of crowded spaces, high noise environments. So this is typically manufacturing, industrial environments where there's a lot of metal. They're either making big metal machines or there's big metal machines all around, and they're trying to track things that are moving in real time. Why ultra wideband is better than other technologies is really that it's a very short, quick pulse with a lot of different frequencies all at the same time. And because it's so short, quick pulse, it just allows us to differentiate the true signal versus the reflected signals at a higher degree than other technologies.
And what frequency range does ultra wideband work in, Logan?
So ultra wideband is considered anything from 3 gigs all the way up to, I think, 10-ish. You guys might know better than me, but it's somewhere around that range, right? So 3 to 10 gigahertz. And that is what's kind of quote unquote referred to as ultra wideband. Now, in that whole band, there are different channels that people operate in, and that can vary country to country, region to region. There's a few different chipsets on ultra wideband, so there's a few different manufacturers competing in the space now. It's a very new space, so there's just recently been more chips made. We're using.
It's quite I was going to say, it's quite an exciting space to be in at the moment, because you must be very excited with all of the new devices that are sneaking in these ultra wideband chips. First of all with Apple, and now we're seeing Samsung. So how long is it before we see it in like Huawei phones and any other kind of mobile devices? It seems like ultra wideband is slowly starting to get a bit more of a foothold in the market. So I bet you're very excited with all of the release notes for all of these devices supporting ultra wideband.
Yes. Well, the old saying, a rising tide raises all boats, right? So it is being adopted. In a way, it's interesting. Everybody's putting UWB chips into phones now, but a lot of it is really just for point-to-point kind of transaction-based distance information. So I can measure my distance to your phone, I can measure my distance to the pay terminal, and I can decide who is actually the purchaser because I have high accuracy in that point-to-point. It works very well for contact tracing, for instance. So we're seeing a lot of interest in that space as well. Our system was developed just prior to kind of all of that excitement. So we've built a system where we're actually triangulating and giving you a dot on a map. So we're not even, the ultra wideband in that sort of sense isn't really even there yet, which is interesting. So we hope to stay kind of ahead of the curve in that sense.
Okay, Logan, so you've mentioned a few very interesting points. First, you said that ultra wideband is, very wide, and that you're using very short pulses, right? So it's like across a very wide spectrum, even like 500 megahertz channels, like half gig channel, I think it is.
It can get all the way up to 900 megahertz wide in certain instances.
Even nicer. So when you have like the multipath environment and you have like a very
quick boom.
Yeah, it's like a click, which you can easily pick up with your ultra wideband access points called the anchors, perhaps. So ultra wideband, why is it better in the harsh environment? It's because of this ultra quick pulse that you can pick up even through noisy environments, multipath environments. It's not like a sine wave. It's like a very quick, like boom. And then you can like measure time of this quick boom. And that is why it's easier to work with this time-based ultra wideband technology when compared to sine wave modulated signal like 802.11 Wi-Fi or 15.4 BLE. So this is the main advantage of the ultra wideband.
So we mentioned that it ranges from 3 gigahertz all the way up to 10 gigahertz. What if I'm a Wi-Fi access point or a Wi-Fi client around ultra wideband? Is this going to affect my connectivity? Am I going to have interference? So do I need to worry about ultra wideband? The new 6 gigahertz range that's come in, do they need to think about it there?
Not at the current moment, but it's an interesting point in that it is a little bit of the Wild West. So in particular in the US, they're auctioning off portions of the spectrum to larger cellular groups. So as it stands, there's really no interference if you're using the particular channels that are registered in the certain countries, right? So using channel 4, channel 5 centers you around 4 gigahertz. It's a 900 megahertz wide band. And it just touches the edge of where 5G is coming in. So there's really not much interference there. In the channel 5, you would be around 6 gigahertz. And again, it touches right near where Wi-Fi would be, but there isn't any interference there. The bigger concern would be for companies like ourselves, would be ultra wideband companies, would be them eventually auctioning off portions of that spectrum. Because we're kind of a new niche technology and smaller, we're having to start to form consortiums to kind of protect the bandwidth that we're utilizing.
Yeah, and also a lot of manufacturing are pushing for ultra wideband because of the using it for unlocking their cars and things like that. So
Yep.
they will be pushing for that. So it also brings in a lot of safety features for mobile devices. I think probably in the next few years we might not even have keys for anything anymore. Won't use a key to open our car, won't use keys to open our doors, and it will be probably more secure than it ever was before.
Right, and so we're very hopeful on our side of the fence as we're seeing industry kind of pick up and see ultra wideband. It's been around a long time, but it's just recently that it's kind of gotten traction. So we have some of those car manufacturers, even some of the aircraft folks use UWB. So we have a few big hitters join the consortium. So we're very hopeful.
I think we've been seeing some Audi key fobs using ultra wideband a few days ago on Twitter, if I'm correct.
What vendor?
Audi?
Audi.
I don't speak German.
Okay.
But it's already there. And another very interesting thing that you've mentioned that I wanted to ask you, you mentioned triangulation. So that will, sorry for like a technical question here, but do you use guys angulation thing for ranging? So do you care about angle of arrival, or do you have like a multiple antenna arrays that are able to do angulation, or do you just use like time difference of arrival, lateration distance based algorithm for calculating range between the tag and the anchor? So how do WISER do it? Because it is possible to use different algorithms in ultra wideband to calculate the XY or XYZ coordinates of a tag. So for me personally, and I'm sure for many people out there as well, it would be very nice to know what algorithms and techniques do you leverage to make WISER work with ultra wideband.
Sure. Yeah. And I can't go too in depth in the algorithms because a lot of those are IP. But suffice to say, we've kicked around angle of arrival a decent amount, and we have some products that utilize that. But our core industry commercialized product is a blend of TDOA and TOF. So that would be time difference of arrival and time of flight information. So it's pretty much all just in the time sphere. So we're using kind of a mixture of those two.
Very nice. So with the mixture of the two, you can calculate XY coordinates. That leads me to another question. Can you calculate a Z-axis as well? Like, in 3D?
We can. Yeah, we can. It's not quite as accurate as the 2 dimensions. We have had live 3D pilots where we're doing more like pallet racking and tracking in those spaces, able to get around, plus or minus probably 2 meters realistically in the Z-axis. So it's probably not accurate enough for something like fall detection. Depends on how open your space is, but it works well for pallet racking, larger items, that sort of thing.
Yeah, definitely. So it's amazing that you can, locate objects in 3D now with XY being extremely accurate. And when it comes to accuracy, how accurate can you say it is when it comes to first the accuracy, like a distance, and then when it comes to the error levels, so like without % of the time and this kind of stuff.
And
right.
How often it updates its location.
Right. So the short, uninteresting answer to that is that it depends. The longer answer I'll give is essentially we're able to, in open air, in like scientific conditions, get down to, about 2 inches or so. But that is unrealistic to expect in the field anywhere.
It's a size that Mac is very, very familiar with.
I want to say the same about you.
That's why I muted first to make sure I got it in.
You gotta get there. In realistic environments, something like automotive manufacturing with welding and metal cages and lines, you're going to get probably more around a meter. So it's really going to depend a lot on your environment. Now, the spacing of we haven't really gone into the hardware yet, but there's obviously the tags that we're talking about right now, the accuracy of resolving the positions of the tags. And then there's the antennas, or you can call them anchors, in the rafters or the walls or the columns. The spacing of those is also going to depend on the space. So for a wide open modern manufacturing facility, we can actually place these somewhere around upwards to 30 to maybe even 40 meters apart if it's wide open, However, in a very crowded, compact industrial manufacturing facility, these would probably be closer to around maybe, at worst, maybe 15 meters away from each other.
And how would I go about, say I wanted to do a design for a WISER ultra wideband deployment? Do you guys have your own planner? Like for a lot of the people listening to this podcast, because we mainly focus on Wi-Fi, they'll be very used to tools like Ekahau or similar tools to model up and design for their Wi-Fi access points deployments. But say if I wanted to do a model for my ultra wideband deployment, how would I go about doing that with WISER?
Yes, and that is definitely a pain point. So we're working towards that. It becomes more difficult in a lot of these complex spaces. The way it happens right now is if we have the floor plans available, we get those ahead of time. We can mark those up, and then it usually requires a few hours on site. We walk the site and give direct placement suggestions. So that's just part of the process as it stands. However, we find in utilizing time of flight information between our antennas that we can do a pretty decent job in any facility of just kind of following a rough grid pattern.
So with time of flight, it's actually quite interesting because this gives us more accuracy than time difference to arrival, right? But that's at the expense of the battery life of the tag.
Right.
Tag must communicate back with the anchor, and it must know more about the anchors than just the IP address. So what is the life expectation of a tag? What tags do you guys use? How do you recharge your tags? Can I use third-party tags? This kind of question.
Yeah, sure. Let's dive in. So our tags, I have one here. I know our listeners won't be able to see it, but essentially this is one of our tags. So powered by a little coin cell battery on there. We make these, so we're not buying tags. We don't use a module. So
just for the listen only ones, when Logan had that held up, it literally fit in the small part of your palm of your hand. So that's got to be very, very small, few centimeters.
Yes, I'm not sure. I would say it's probably the size of maybe two CR2032s stacked together, maybe just a few things like, we have quarters here in the States, but easier.
So probably a 50p coin or a £2 coin here over in the UK. But with it being so small and lightweight, that could pretty much go onto like anything. So like a lanyard for people walking around, or have it like on a belt maybe. So yeah. What do you what's the kind of normal object that you would put one of these tags on?
So we have put them on a lot of different things. We allow end customers or partners, we give them the DXF, the board outline, if they want to make their own form factors. We do provide kind of rugged industrialized form factors as well that you can just fasten. They're very light and very small, as you mentioned. So anything like Velcro, industrial Velcro, you can pop it on and off pretty much anything. That being said, they are not small enough to fit on individual small tools. So that's been a lot of where we've had problems is I want to put this on, say, a socket wrench, make sure it doesn't get left in a transformer and an engine. That is where something that with an active tag falls short. So our tag has to be big enough to hold a battery, as Mac was mentioning, and so it won't quite fit on those individual pieces. But we've put it on a whole bunch of other stuff.
Okay, so if the battery dies, we have to replace the battery, or is it rechargeable?
Right. So they use just off-the-shelf CR2032 batteries. So in bulk, they're about, I don't know, like 10 cents or something like that. They are user replaceable, right? So our form factors are able to just be pried open, and then you can slot another battery in. They're meant to last a long time. Battery management, as I'm sure you guys are aware, can be a real hassle if you have, let's say you have 2,000 items and the battery life is, 2,000 days. Well, that means that you're replacing a battery a day. So we're using as much as we can. We're utilizing a low power state on this tag. So we're really just trying to wake it up, chirp, and make it go back to sleep. And ultra wideband comes into play there because the chirp is so quick. So there's two chirp rates on the tag. There's the I'm in motion chirp rate, and there's the I'm resting chirp rate, right? So both are configurable. At max, we can get up to, I think, 10 hertz active. So experimentally, I believe we can get up to somewhere like 40. But in practice, that's really the highest we've gone is about 10 hertz active. And resting can obviously be very, very, very slow. And for a rule of thumb, if everybody wants to get out their Excel sheets, if I'm chirping once a second and I'm moving 8 hours a day, so 1/3 of my day, 8 hours a shift, I am moving and using that active rate. And my active rate is once a second. Our battery will last about a year and 9 months off of CR2032. So we've attempted to maximize battery life for an asset management perspective. So you're not going to be wanting to run around and be replacing batteries. So obviously, if you're chirping double that speed, you'll last half the time, et cetera, et cetera. But that's a good place to start your calculations.
And also, like most of the assets, they won't be moving all day, right? So you probably have some battery saving mechanisms. If it doesn't,
right? That's the two
frequently.
Exactly. Yeah, the two chirp rates are used for that. So if it's at rest, we'll just go to the resting chirp rate after a few seconds, and then we'll be really, really. I mean, if you're chirping only once every, even just 10 seconds, your battery is going to last
forever.
Years and years.
So that sounds to me like a massive advantage, like not only in terms of like a spectrum, how it's being used, wide, low power, and very, very quick chirps, but it's also great with tags and battery lives when compared to competing technologies with active tags, like Wi-Fi and BLE. They won't last that long, right? There are some competitors in the market with passive tags like RFID and stuff, but this will not be as accurate, as quick, and as sexy as ultra wideband. Not even close. It just has no battery, but it has a different use cases to ultra wideband. And it seems to me that you have some more sophisticated design of your tags. Like if they know when to go to sleep, they must know that they are moving or not moving. So how do they know that? Do you have some more sensors in your tags?
Yes, we're utilizing a very simple low power motion detector on the tag. So again, just trying to minimize the amount of power used. So it really is just, am I moving? Am I not? So it's just a very, very simple motion detector.
Okay, that's amazing. So the tag was like, I don't know, it looked like in a camera, like it's 2-3 millimeters thick. So it probably would even fit in. Yeah, exactly. It's very thin. So it probably would even fit into a card form factor that you can wear. It's amazing. So to detect these tags, what do we need? What else do we need from the infrastructure perspective?
Yes. So as I was mentioning earlier, the tags are going to be put on the asset and they're kind of chirping, but there needs to be something to receive the signals in order to figure out where they are, right? Point at them and triangulate them. So we have what we call antennas or anchors. We kind of use both interchangeably. And we tried to make something kind of inexpensive and simple. So these are our antennas. I know the listeners can't see that, but essentially they're just kind of small.
Looks like a little swan.
Yeah, it's an odd form factor. It was intentional. So again, these are all designed in-house, made by us. The real the real brains here are up in this head, and then there's like a stalk that comes out of it.
It looks like a coat hanger.
Yeah, we've had less. We've had some colorful adjectives thrown this way, this form factor. But basically, it is an antenna designed by us. So
is it omnidirectional in this one, or is it a directional one? Can you get different types of antenna for your?
Because we're doing meshing between the antennas, we are trying to be as omnidirectional as possible. So like as close to omnidirectional as is possible in the RF space. So these are all omnidirectional antennas, and they have to kind of be able to communicate all around them to each other in the mesh. We have some conceptions of unidirectional antenna ideas, but for our commercial sold units, it's all omnidirectional.
Okay, cool. And any Wi-Fi guys listen to this, just think of anchors the same as access points. That's how we refer to basically the ultra wideband access points. They're called anchors. So if you hear us talking about anchors, just think access points.
Right. Yes. Our system is basically needs power. So each of these antennas need power, just like an access point.
And how much power do they need, Logan?
That I was about to say that being a primary difference in that they only need 110 milliamps. So pretty low amount of power on a per antenna basis. So what we do in commercial and industrial environments is actually a daisy chain these antennas together back to our little gateway box.
How many? So we can daisy chain?
10 maximum.
And then that goes into your own. Was that one of your own adapters? Can it go into like a PoE switch or?
You got it, exactly. So this terminates at the PoE switch, right?
Okay.
There's two outputs, right? So I can have a chain of 5 and a chain of 5, a chain of 4 and a chain of 6, that sort of thing, going off of the gateway. And so each of these gateways would be given an IP address through the switch. So the WISER system has these anchors, they're all talking in ultra wideband, and then they're sending their information back through the gateway.
Does the gateway determine which anchor it's heard which tag at? Because obviously it'll be coming all through the same port on this. You could have 10 anchors coming through the same port on the switch. I'm not sure the switch will be able to determine what that is. So is it the gateway that does that kind of bit of intelligence before it gets to the rest of the WISER infrastructure?
The gateway is... Calling it a gateway might be a misnomer to some degree. It's really just kind of, it's grabbing messages and routing them, sending them different ways. The antennas themselves are doing a lot of timing. So they're kind of gathering timing and then sending that timing back. The gateway is grabbing all of the timing information that's been stamped and sending it over to some computational device that then crunches it down.
Okay, and if I want to power 10 of your anchors from one port out of a PoE switch, what power do I need to have for my port to be able to do 10?
Just standard PoE, whatever the standard PoE power is. I don't know it offhand, unfortunately. So.
Okay, no worries. So yeah, that's interesting. This and it saves a lot on. So sometimes for manufacturing companies or other large warehouse commercial spaces, the cost for per port and cabling can be quite expensive. So to know that you can daisy chain 10 anchors off of one port would be I imagine, quite attractive for some of your customers.
And it seems to me like we could probably leverage our, beloved PoE pass-through that is built into some of the access points. So it probably is possible to connect your anchor gateways, whatever it's called, to an access point and have Wi-Fi and ultra-wideband being powered from even the same port on the switch.
It is.
Even extra more savings. Amazing. And guys, like the antenna, the anchor, it looked, for the listeners that don't see video, it looks like the coat hanger, but it's a good thing because it has like a bracket attached. So we don't have to worry about the distance from the wall, distance from the ceiling. It doesn't matter, right? It's like it's pre-attached. It's one part. So we just like use two screws to screw it into the wall and job's done. Because
we learned the hard way, didn't we, Mac, when we tried to install an anchor too close to I think it was your fridge, and it was skewing our data results because of the back lobe effect of the being too close to material. So that's a very good design that you've done there, Logan, to consider that.
Yes, yeah, you need to stay a wavelength or two away from anything. So that bracket is purposeful, exactly.
Yeah, because it really does skew the results. We had a massive difference from when we first installed it and we tried running it around to see what the accuracy was like, and we were like, oh, this isn't too good. And then we spoke to the guys and they're like, yeah, you need to pull your anchor out slightly, even if it's just a few inches. So you got your nice knife and fork trick and balanced it and pulled it out, and then the accuracy shot up massively. So it's massively important for ultra wide band deployments.
Yeah, it's very sensitive to a placement. Does it matter if I put it like inside out or the other way around?
As long as this flat section of the antenna is parallel to the ground plane,
yeah,
should be fine. So this orientation is not correct. So if you were trying to install it from a rafter, you would simply want to rotate the antenna to make sure you can mount to the ceiling.
So that's another clever trick. So you have like 45 degrees rotation built into the antenna, so you can still attach it to a ceiling, rotate it down, and it still works. Great
Correct.
Stuff. Okay. Yeah. What would you say would be the highest distance from the ground level that you could install this omnidirectional anchor on? Let's say in an industrial space in a warehouse where you have, just imagine, I don't know, 20 meters high racks and tons of forklifts running. What would be the highest distance?
So in industrial environments, we have not hit a limit in our deployments for ceiling height. The reason being that up on the rafters, you get a much more direct line of sight between antennas and between the antennas and tags on the ground. So there typically is not a ceiling that's constructed high enough to be a barrier to deployment. However, the range between antennas is limited, right? So eventually you're going to reach a point where the distance between the floor and the ceiling is too great for the tag to reach. So the tags can really only chirp out, and we could probably only hear them at like a very maximum distance of like 250 feet. So in meters, you have to do the maths, like 80 something. So, there really aren't that many ceilings built that high. So that hasn't really been much of an issue yet.
Okay, so this leads to my next question. So you feel like there is really no need to have directional antennas in ultra-wideband tags? Well, if you can install them like even 10 or 15 or 20 meters above the ground, then it probably makes little sense to use directionals in these examples. But do you have any plans, or have you tried using directionals?
Yeah, I think you mean the anchors, not the tags, right, Mac?
Yeah, sorry, of course.
Yeah.
Yes. So we do have some early stages of directional antennas, but as it stands, it's all omnidirectional. There hasn't been a need yet.
Okay.
And
Easy.
what I think we might have skipped over this, but did you mention like what chipsets you use in your tags and your anchors, or did you want to just talk about that briefly?
Right, yes. So there's a few different chips in the marketplace. We are currently using the DecaWave tag, which is now purchased by Qorvo, so Qorvo tag.
And they actually come from quite close to us. They're from Ireland, right?
And now they're right close to us, weirdly enough. So Qorvo purchased them, which is like an hour and a half from us right here. So very strange.
No longer in Ireland?
Well, I mean, DecaWave still is, but they were just purchased by a larger organization. So.
Okay, very interesting.
Yeah, the market is moving. So as you mentioned, people are gaining interest in ultra wideband. So it's coming out. They're starting to put it in phones. So there are other ultra wideband chip providers. We've been very satisfied with DecaWave's performance. If there was another that worked similarly or better, we'd be interested in trying it out. But as it stands, it's worked well for us.
From my perspective, it's quite difficult to imagine having anything working better than DecaWave chipsets. We've seen them in action multiple times actually now, and it's like super mind-blowing. As we will see in a sec in a demo, even it can register like a movement of your hand with a tag, like a slight movement. It's absolutely smashing.
Yeah. We're very satisfied with their performance.
Yeah, not only.
You're probably hoping that they don't put it into the Apple Watches then, Mac.
Well, I wouldn't mind having U1 chipsets everywhere, in consumers' devices being open for us to use. What I heard is like Apple is releasing something called the AirTags, I think, that would be trackable by the U1 chipsets in the phones, but it's probably not relevant to the RTLS in our space, because we won't be putting, iPhones out there as anchors around the walls, right? It's probably too expensive to be sitting as an anchor to locate Apple AirTags. But yeah, it's really nice to see that the market is using this technology more and more. And also from the security perspective, it's so amazing to use ultra-wideband for the keys in the cars, because I cannot steal your identity, right? It measures the distance, so you have to be standing next to the car. I cannot open your car by knowing the code of your fob while sitting in the forest 200 meters away using directional antennas anymore, because it doesn't care about the fob ID. It cares about the time distance. So that's really cool. So guys, since we've already discussed quite a lot of technicalities of the ultra wideband and suitability for harsher environments with multipath, with higher ceilings, manufacturing, automotive and stuff, can we spend a few more minutes talking about the use cases? Like, did you have any real environments that you've put the WISER system in that you would be able to talk through how it looked, how it worked, how many anchors you used, what is the amount of tags that you can track simultaneously in these environments? I think that will be quite interesting. So the more you tell us about this, the better, I believe. So let's just pick one of your favorite deployments and spend a few minutes there.
Sure. Yeah, as you mentioned, there's a big difference between scientific curiosity and an actual implementation reality. So those are very good questions to ask. And a lot of what we've had to work against is these sorts of RTLS or magic hand waving systems not really working in reality, especially at scale. So we've had to work against that conception as well. So I can go off a few, some of our larger ones, and then I can work backwards. But what you'll see here later in our offices is just just kind of a standard office space would just be around 5 antennas or so. So pretty easy to do that computational math, easy to get it calibrated, so on and so forth. But when you get up to like 200 antennas, that becomes a lot harder to calibrate, a lot harder to get going. So we are in live running meshes right now. I think our largest active is in the upper 100s, like 160, 180, something like that, of contiguous antennas. So in one building, they would all be talking in one singular mesh. Beside that building, you could have another building of another 160, 180, 200 antennas. Our engineers guarantee we can go much higher than that, but I'm speaking from implementation side. That is the most amount of antennas we've had. Those are all synchronized, all talking, all creating one big mesh.
And just sorry to interrupt you there, Logan, a question that just popped into my head when you talk about, these 200 anchor deployment potential that you do via mesh. When you comes to your map calibration, I know we spoke offline about this, but I thought it was quite impressive as how you, if you didn't mind just putting in there how you guys calibrate where the anchors are on the map and how they know where they are in their positions and how they talk to each other, because I think the listeners will find that very interesting.
Sure, and we can go over a bit of that in the demonstration as well. I'll refer to it here, and then we'll dive in a little bit more when we see it in detail. But for the listeners who aren't going to see that, essentially, we've tried to make it a lot simpler to install this. So we wanted to avoid people going in and laser measuring and going in with RF and trying to figure out spectrum in different areas with directional antennas. So it's intended to almost be, you go in, you kind of grid it out. We walk the facility with you, say, hey, probably that column, probably that column. If it's not that column, it's not the end of the world. You can probably put it on this other one. And we'll do that throughout the facility. And then in our program, which you'll see later, you load in your floor plan. And then you actually physically just click and drag the numbered antennas to where they are on the floor plan, or where you think they are. And then once you boot up calibration, the WISER system will actually kind of rectify where you've put each antenna to a certain degree. And through that process, we can actually do a 200 antenna mesh in probably about half a day. So it's, it takes some time. You want to split it up and kind of do it bit by bit, but you can get a whole huge, 500,000 square foot facility done in short amount of time through that process.
And if you just compare that to a Wi-Fi RTLS deployment, where you not only need to record what way the access point is facing, the height, the orientation, like you said, get that laser measure, like exact detail, very particular of exactly where the access point is, and you still don't get the accuracy of what ultra wideband does, and the fact that it's simplified and you can just drag and drop them onto a map. I've been doing RTLS for a while now. That is massive for any implementation engineer, because just even recording where the access points are and getting the installation team to install the right access points in the correct positions, to the correct orientation, to the correct height, making sure they're facing the right direction. Like you just said, you can do 200 anchors and 500,000 square foot, or however big you just said it was, in half a day. Man, it would take days and days and days to do that for a typical Wi-Fi RTLS deployment.
And also look at the human error element. How many times we didn't do a good job in like putting the orientation in azimuth plane.
What do you mean we?
I mean, okay, me in my lab. Well, and that can still happen, right? So I don't want to say that it's devoid of mistakes that can occur in implementation, right? So people can still hang antennas sideways, even with the brackets that allow you to rotate the antenna, and there are still errors that can occur. But in terms of calibrating and getting the mesh calibrated, that's a pretty quick process. They still have to get out there and physically place the antenna on something, and that can take a while, depending on the contract crews you're bringing in. Okay, so another two quick questions. First of all, do you care at what height, a difference of height of the mounting of the anchors you put the anchors on? Do they have to be on the same height, or you can have like some differences between them? So in our program, you would enter in the height at which it was hung. So we don't really care if they're on the same plane or not at all, as long as you just record it as you're hanging it up, what the distance was, to a relatively accurate extent. You don't have to get down to the inch, but that's quite well. Not everyone does that. So that's quite nice. So you have this flexibility of mounting of the omnidirectional antennas, which is nice. And the second question is, how do you time synchronize all the anchors? Like if you have 200 anchors, do you have like some anchor masters that they synchronize to their peers? Do they, I wanted to say slaves, but it's no longer a good word in the technological world, is it? So if you wanted me to tell you, you'd have to pay me a bit more. But that's a lot of our system and the intellectual property that we have is in being able to time synchronize 200 contiguous antennas across the facility and get time stamping that gives you accuracy down to what we do. It's a very hard process. But you're right, you're along the correct path. Essentially, you need clocks, and they need to be able to distribute that clocking information throughout the mesh.
Because I remember from our initial conversation that we had, there's quite a lot of unique ways that WISER do things different to other ultra wideband partners, which I'm sure you'll elaborate on further down the line on this podcast. But I was quite interested to hear some of those things that you guys do, especially around the line of sight.
Yes. And a lot of that is in our algorithms internal to the system. So I am not really the appropriate one to discuss, but essentially what we've attempted to do is have the system determine whether it's blocked by a wall or blocked by a body and correct for that. And that's using statistical analysis to try to determine that. So we're able to penetrate interior walls to a good extent. I would say probably 2 or 3, depending on the construction. So you could probably get through 2 or 3 interior just drywall, wood stud, or metal stud walls. Cement walls, metal obviously is a lot more difficult. We are able to get around metal to a certain degree for non-line of sight. A lot of the rest of our algorithms are for that clock synchronization that Mac was mentioning. That's very important and difficult to do. And in particular, it's very difficult. It's transparent to us as designers, integrators. We don't care about the clock synchronization at all. It's being done transparently. It's been made to be set up by anybody, a layman, essentially. So you, as a developer, what you will receive are coordinate points. That's really the only. And there are ways to, obviously stop and start the mesh and queue calibration and move antennas around through the API. But really, our API access is to deliver you the coordinate information already. So all of that is done internal to WISER.
Nice.
Yeah. So it is a challenge to do all that at a low computational load. So we've attempted to keep this very lightweight. So this is all, we mentioned the antennas, we mentioned the tags, all that information is getting sent through gateways. You do not have to have Ethernet connected to the antenna. You can have some antennas just powered off solar or battery packs, right? So you can have a hybrid topology of your mesh, as long as you have a few networked antennas in there to get the data back. And that will come to the WISER software. That's where we're talking right now, where there's a lot of that IP that's generating all of the information that needs to be sent back through the mesh, clock synchronization, algorithms for non-line of sight. That all is running on right now as a Windows application. And we are able to run decent sized meshes off of like a USB compute stick. Essentially, if it can run Windows, it should be able to run our software.
And I presume this all has to be kind of local to the infrastructure, and then this feeds something back to maybe like a cloud solution, or say if I deploy WISER at my office in London, how do I view that remotely?
Yeah, so depending on the partner integrator in that case, or the end client. So a lot of our aerospace or defense end clients would prefer this to just be on site, and so they're running just a Windows virtual machine on a VLAN on site, and the data never leaves, right? So as long as the WISER software can communicate again to these little gateways with the IP addresses, the WISER software can be off site. We have instances where it's hosted in AWS or something else, as long as it can communicate to these IP addresses.
Do we have any best practices when it comes to the RTT?
Not particularly, but you definitely want to keep latency low. We've been tested at a large amount of latency. We early on in our projects, we had a facility that was running it was in Louisiana and the server was in California, and so we were tested pretty early on with low latency. It's a very old system, okay. But we've been built to handle a pretty extreme amount of latency. Obviously, that would mean you can't be used for extreme real-time use cases, right? As you're going to have seconds delay between when somebody moves and when you're notified of that.
Yeah. So all that is affected by the latency, I guess, would be just the blue dot on a map in your location engine, like location system, since the anchors, they capture the timestamps of the chirps of the tags. So even if it's being delivered to the location system, location engine 5 seconds later, it will just display it on the screen 5 seconds later, and that doesn't change anything, right? It still works.
Correct.
Okay, that's great. So I think like we are getting to the point where I'm quite eager to see WISER system in action. How about you, Matt?
I'm dying to see it.
Okay. Great. So Logan, if you wouldn't mind showing us a little bit more in a real world now, we'll be trying to translate it to the listeners only. But guys, if you have a chance, come over and see it in action because it's worth it.
Great. Yes, and I'll try my best to explain to the listeners as well what I'm doing. But I'll share.
Would you mind? Yeah, if you can share your screen, I'll bring that into the video.
Yes. Let me share here. Okay. So I'm sharing my screen now. It's just a floor plan. I am in the bottom right-hand office. I've got a bunch of tags behind me on the desk there. So you see them all as kind of a red blob. There's a bunch of individual ones here. I can zoom in. So there's 4 tags on that table. And then I have 2 in front of me and 1 on my right, which I separated because that's the 3D tag. So if we have some time, we might could do some 3D later. So I've got 2 with me. So we mentioned earlier, it's basically there's antennas that go up in the space and there's tags that go on the items. We're using a gateway box basically to communicate to this system, and That's really the core of it. So I'm running it's a Windows program. It's doing all this calculation. I've started at the endpoint here. So I'm already all calibrated up and I'm tracking tags. And you can see I've got 2 tags with me. You should be able to see me on the screen, one in each hand. So even if I just kind of separate my arms here, right, you can see me on either side of my chair and just kind of come back together in front of my face here. So in these sorts of indoor environments, we're able to get, accuracy of, we're definitely probably under a foot, but again, it's going to vary depending on where you are in the facility. We only have one antenna that has direct line of sight to us right now. The other antennas are out in the environment. So I'll show you what I mean by that. These grayed out antennas are what we've put up. One's in my room, and the others are out on this floor plan. So for the listeners, I'm highlighting where the antennas are in my space. So you can see they're about 50, 60 feet apart. So, maybe 20 meters max. They're pretty close together in this environment. So, and what I'll do is actually back up just a bit and kind of show you what I meant by the calibration, all of that sort of stuff earlier on in the program.
Yeah, we can see them in red now, so it's a bit clearer and a bit easier to see where they are on the map and just physically the distance between them, which is a bit easier now. Yeah. And we will shortly be bringing
about the distance between the antennas. I think it's a madness in terms of how little amount of antennas we have here and how well it works throughout multiple walls. What do you feel?
So thank you. Yeah, we've again tried to make sure that we can do through wall transmission, right? So you can see it for our viewers here. You're going to look at the office. We really only have one antenna that has direct line of sight into this office. The remainder, 4, 2, 3, and 13 are their corresponding numbers, don't have direct line of sight to this office. In fact, 2 and 3 are having to shoot through 2 and 3 interior walls to get to us. And so the tag is actually able to reach out through those walls. And when I walk in a little bit, in a few minutes here, I'll walk outside. I'll be sure to walk into the other offices and in the kitchen just so we can see that more in reality. But one of the core competencies of the WISER system is what I was mentioning before. You have a lot of antennas. You need to calibrate them all. They all need to be time synced. We attempt to make that as easy as possible. So in a given facility, I've loaded my floor plan at this point. I've started placing my antennas on the map. Even if I don't really know exactly where I placed these antennas, right? If I lock a few into place, that I know for sure this one's in the office and I know this one's over there on that column, I'm going to take the others and I'm going to calibrate them, right? So I'm going to say, WISER, calibrate this system. And so what it's going to do now through an iterative process that I'm just going to automate by pressing spacebar is it's going to try to rectify their positions over time. And you'll see they'll start to shift in time, right? So we're starting to see the antennas shift back to where they were on the wall. So for the listeners, basically I'm going through, the antennas are all using time of flight to try and kind of move themselves back into position, right? So now I've calibrated the system. So it takes a little bit of time. This was only 5 antennas, so this took maybe a minute. Obviously, if you have 200 antennas, this will take longer. So this will take maybe 10 to 15 minutes. You would split it up into sections to make it a little easier. And so, like I said, you'll end up, this process can take, half a day or more for very large, 500,000 square foot facilities. So,
but that's still very, very impressive and very cool to see.
Yeah, we're just sitting here smiling, I think, like all of us.
Great. Yes. No, thank you.
So Logan, you had to just one anchor. So I can see out of 5 antennas, one has a rectangle around it. Does it mean that this is the antenna that you verified its physical position, that you know that it's there in that corner of the office, and then all the remaining antennas that will be calibrating themselves in relation to the one in the bottom right?
No, so that actually is an icon indicating that that's the connected antenna to the IP box. So not one of these is actually rooted in physical reality, although you very easily could do that, in that this is all on a coordinate grid. So if you know the coordinate position of an anchor, you can go ahead and place it in that direct coordinate and lock it into place, right? And so you would lock these guys. I calibrated the others. I only did it for 5 antennas here. You could do this for 50, 100, 150, 200 antennas. It's the same exact process. It just takes a little longer. As I mentioned before, each one you do need to enter in the height, right? So that has all been entered already. And then I'll switch it from calibration to tracking, right? So I'll say, hey, you've calibrated. Now it's time to configure into your tracking mode. So we'll wait a few seconds. It'll tell us that it's synchronized. And then from there, we can just go to tracking. So I can say, all right, we'll run tracking. And then all of these are on resting ping rates, the ones on the table. So they'll take a few seconds to pop up. These are in motion. So obviously they're already here. And we'll see all the tags pop up. So go ahead.
No, I was going to say, if we're ready for the demo, I will bring in Stephen's camera so we can see when you leave the office and then go down the hallway, and then we'll be able to see on the map the red dot being updated. And I think it draws a line as well, right, to show where you have been updating?
Yes. Yeah, I toggled the history here. So you should be able to see a yellow line of where I'm moving. I'm going to move, I'm going to walk out in, you should see me on the other camera. So I'm going to mute this mic and move to the other.
Stephen, your camera has just gone off. There we go. Then I'm going to drop you off now, Logan, and then bring Stephen in. Okay, so now we can see Stephen just standing there. Perfect little model. He lifts a wave. There he is. And we should be able to see Mr. Logan walking. Yep. You can see your hand with the tag. You stopped. Nice little twirl around the office as he's walking around, and we can see his position being updated. I can see you moving through into an office now, and the path that you're taking is being updated very, very frequently. You must be obviously now going around some office chairs and table, about to come back out, but we have lost your video, Stephen. There we go. Thank you. No worries. So Stephen's now going to be giving us a bit of a demo, walking around.
So can you guys hear me okay?
We can hear you.
Awesome. Yeah, so basically just wanted to walk around in kind of a non-line of sight environment there. So you can see there's no antennas that have any sight line into that office. So there is some discrepancy between our measurements here. But overall, you should be able to, there we go. Sorry, I cut the camera on accident. But we'll see Stephen moving around here. I'll go ahead and move to the other microphone, and so I can answer some questions on what you guys are seeing. But essentially, this is one tag chirping at a pretty fast rate. I think this is at 2 or 4 hertz, so pretty quick.
So 2 or 4 hertz, it means just like 2 or 4 times a second.
Correct.
It really looks like a real blue dot experience that is very fast. So I don't see many scenarios where you really need to have faster refresh rates of the location of a tag.
No, typically not. This is really the max we've ever deployed. Most folks are actually significantly lower than this in that sense.
Makes sense. And also, like, we've discussed all the harsh environments in manufacturing and warehouses and production lines and stuff, and we are now in the enterprise office. So it's not only, limited to more difficult environments, it's perfectly suitable for the enterprise environment as well.
Yes, yes, it is. We think so. Let me switch over to the other microphone here. And for those wondering, we are not wearing masks, but we have been sheltered together here at the office. So we're both in a COVID pod together. So.
Okay. Thank you very much, Stephen, for that demo. I will drop you off the video now, and we can just go back to Logan's screen.
And guys, just like very quickly, I'm looking at the tags location, and it's so mad. We have one tag in the like, I don't know, 5 by 4 meters. We have another tag outside of the office, just maybe 6 meters away, and then we have 3 other offices in a line, and then another tag on the other side of few walls. It looks like around, I don't know, 15, 20 meters away. And the farther tag towards the back of the office, it looks like it's around, I don't know, 30 meters away, 25, 30 meters away. And with just 5 tags, we have such an amazing accuracy. So quick question to you, Logan, like, do we need to have 5 tags? Would it work with 4, or do we need more for error correction?
It would work with 4. Theoretically, it would work with 3, and that's where we typically draw the line with error correction. But yes, it works with 4. We've added a 5th here because we kind of have an odd-shaped office. But again, this displacement, what you're seeing, the distance between the antennas, is going to be variable in your environment. So in a larger open manufacturing space with high ceilings, you can actually get a lot further than this.
And that's quite amazing. So 3 minimum. If you have more in one geographical space area where all the anchors, they can hear each other, you will have better accuracy, perhaps with more error correction, right? Where you will have like more more circles intersecting with smaller error areas.
Exactly. So if you have more antennas, it's typically better. More antennas, the better is usually the case here. So what I'll do is I'll zoom in. So one really great thing about this system, not to boast too much, is the consistency in measurement. So these tags behind us have not been moved. I don't know if it's easy to see that up for the viewers, but basically these are stationary tags, right? They haven't been moved, they've just been sitting on the table, and you can see there is some variability in the measurement, right? As they're chirping at their resting chirp rate, they're kind of bouncing around. But if we look at the colored dots and we look at the scale underneath our screen here, that is 1 foot, and I'm sorry we use American units, it's very frustrating, I'm sure, but that's 1 foot. And so we can see that all of these points are encapsulated by, 0.5 meter or less in terms of, and we don't have the drifting problems that other technologies might have.
Yeah, so just by looking at it, like the error in distance calculation accuracy, it looks like around 0.5 foot, maybe.
Yeah, and that again is gonna depend on the environment, right? So if there's folks listening here that are like, oh man, I have this industrial facility with all this metal racking and I want to get this accuracy, we might be able to do that, but it's more realistic that you'll probably get, 0.5 meter or 1 meter, depending. Obviously, that depends on your facility, but we're usually always under 1 meter.
Yeah, we were trying different vendors of ultra wideband in our perfect lab environment, which was like 9 meters by 7 meters with 5 anchors with direct line of sight, and we had some crazy results with just inches accuracy, which is crazy. But no, you're right. You have the same amount of anchors spread throughout the entire office that can host how many people, like 30 people ish, just by looking at it, and it also works with great, amazing, mind-bending accuracy.
So this would be great for contact tracing if you want to try and get people back to the office and make sure they stick to that 2 meter social distancing. If they've come into contact with someone who unfortunately may have contracted COVID, you can go back and look at their path history to see who they may or may not have overlapped with, or if they've spent a certain amount of time in a smaller office, then you can ask them guys to self-isolate. So I think this is massively going to help and be a big part of our lives in the future, because let's face it, COVID isn't going anywhere for a while, is it? So we need to figure out ways that we can get back to some form of normality, and using systems like this I think is great, because this is going to really help businesses get back to kind of operating in a way that they're used to, and can safely track and trace people's movements and keep people as safe as possible.
But don't only go back with confidence, because if you use less accurate RTLS systems, if you have like 1 to 3 meters accuracy with BLE or with Wi-Fi, actually with BLE you can get better than that, but with Wi-Fi, is it super helpful for you if you have like a room accuracy or like a zone accuracy? For COVID, it might not be enough, but with this accuracy, it's like super accurate. It will be amazing for the business to understand exactly the flow of people throughout the facility.
Yes, so that's one thing that we're trying to push, is basically, well, you can certainly get contact tracing in the sense of just a point-to-point beep with other technologies. But once COVID is past us, which fortunately, hopefully will be soon, now if you have a WISER infrastructure or some other RTLS infrastructure in place, you can take the tags off of people and start putting them on machinery or work in progress or carts or parts, whatever you need to put it on, and then utilize it for a further purpose than just its temporary purpose. And you can't really do that with other contact tracing methods.
Exactly. And just a very quick question, like we know that ultra wideband is not yet as popular as the Wi-Fi or BLE RTLS because, like, few different factors, like BLE and Wi-Fi is built into vast majority of the devices that we might be using in most verticals, and ultra wideband is either not there or it's locked, like in iPhones, let's say, that we can't use it as a tag yet. But it's definitely getting there. It's getting cheaper. It's getting easier to deploy. So how costly is ultra wideband when compared to other technologies? Is it like a very steep price, or is it getting more practical for us to start thinking about deploying it in, like, across multiple verticals?
Yes, and that's a great question. It's still typically a little bit more expensive on a per tag basis. We've tried to make every other aspect of our system and ultra wideband systems less expensive. A traditional ultra wideband system from legacy like Zebra or something can be very expensive on the infrastructure side as well. But for WISER, it's really the tag cost that's still pricey, right? So we're at, depending on your Bluetooth vendor, we can be anywhere from 2x or 3x. So on a tag price. But in terms of infrastructure, our antennas are relatively low cost and the software is relatively lightweight. So essentially, we're able to compete on an installation level usually with other technologies. So it's going to only get less expensive in time. But as it stands, we're actually relatively competitive for medium to large size manufacturing facilities.
That's amazing. And say if I wanted to integrate WISER with some other solutions, how would I go about doing that? Do you have any APIs, or how can we go about integrating you guys with some solution that we're aware of?
Yes, we do. So we have APIs as well as a direct to database link up feature. So we can take the tag endpoints and just dump them into a database for you to do what you will with. So we have two real direct routes to market. One of them is obviously through channel providers that have a front end and have some business logic and run with that. So they're just utilizing our API. They sit between us and the customer. A lot of our direct to consumer sales, what we're doing is actually just giving them the raw data and they're integrating it into their existing ERP or their WMS or whatever they're using. So say I already have SAP or some inventory management system. Well, if you have WISER running in the background, they actually end up never even using our graphical interface. They just set up they use our interface to set up the antennas. Beyond that, it's live coordinate and zone-based information streaming to their backend so that their inventory can automatically update its location. And so all they do is they just log into SAP. They don't even have to know WISER's running, and the location is always live.
Which, right. I mean, for me, if I was a end user consumer, that would be hugely beneficial for me, because then I only have to work with systems that I'm familiar with and I know, and I don't have to worry about learning a new system. That
has been the thought process there. We're trying to not focus our energy into creating a fancy front end with lots of logic, and more so just the core competency of the technology. So synchronizing the antennas, getting coordinate data accurate through walls, non-line of sight. We're more of an engineering house than anything. And so what we've done is we said, hey, if we can get you the coordinate data and we'll help integrate it and put it exactly where you need it. Typically there's a small integration portion where, what databases are you using? What do you need? We'll send it right there. But yeah, they don't want to learn another system. And in 10 years, when WISER Systems is obsolete, they've built the business logic around RTLS and they can replace us with the new game in town, right? So it works well for both of us, to some degree.
It really feels it, and I can see and think why that would be great for the end users. Is there anything else that you wanted to cover, or anything that we've missed that you wanted to mention on the podcast today?
Oh, I'm sure there's tons of stuff we forgot. But no, if anybody wants any additional information, please, you can go to our website, enter in a form, talk to one of our associates on staff here. You can also email me directly if you feel inclined, which is my first.last@wisersystems.com. And I'm sure you might be able to post some of that, Matt. So.
Yeah, we'll put it everywhere. But yeah, so just if you want to give your contact details, if you're happy to give them out there, then we will share it with everyone. So I know you guys, you said earlier on at the start of the podcast that you're licensed to sell in America, and it'll be coming soon to Europe. So say if I'm a European customer and I'm interested in WISER, how would I go about finding out more, contacting you guys? Is there going to be a European distributor? How will it work?
So we're legally allowed to sell in Europe. What we need to produce is the declaration of conformity for using our spectrum in Europe. So we can sell direct to you, but you're not allowed to set up a full site until we have that declaration of conformity. So you're allowed to do pilots at this point in Europe, and we have a few. We have one in Ireland and one in England. But at this point, you're not allowed to do a full facility until we get that in place. So that'll be probably about 2 months from now, definitely this year. So we're working on that. So I would encourage people in Europe to reach out because by the time we get something going, we'll likely already be able to just ship you stuff.
Sounds amazing. Well, thank you very much for your time today, Logan, and Stephen in the background for his help with demoing the WISER solution. I personally think it's a great solution, and I think it's going to be massively important and helpful for going forward with this whole COVID contact tracing. I think I know that in mind these were probably this solution you guys were probably thinking is going to be more manufacturing, harsh environments where Wi-Fi and BLE doesn't work too well. But given the current climate, enterprise offices, shopping malls, all of these kind of environments, I think will really benefit from having a solution like this to be able to help safely get people back to work with confidence. So I really hope and wish you guys the best, and hopefully you can see some WISER deployments around the UK in the future. We would love to be involved and help you guys out with that. And we will share all of your guys' contact details. So if anyone would like some further information, maybe a demo or a POC, they can get in contact with you guys. But thank you very much. We've very much enjoyed the podcast today. And like I said, anyone that's just listening only, please, even if you've got a spare 10-15 minutes, just come on and onto the YouTube or our website and watch the live demo. It's really, really impressive seeing how fast these tags can update their position, and the accuracy is mind-blowing. So
yeah, thank you so much, Matt. It's been really fun.
All right, thank you very much, guys.